It turns out that continuous functions are really nice in a lot of ways, and combining continuous functions is nice. Um, Here's some properties of these continuous functions. So suppose I got two functions f and g, and they're both continuous at x equals a. Of course, by definition, that means that the limit as x goes to a of f of x is equal to f of a, and the limit as x goes to a of g of x is g of a, right? That is, the limit as you get close to a is the same thing as what happens when you actually get there, okay? So suppose those two functions are continuous at a, then so is the function f plus g, right? If you add two functions together, two continuous functions, you're going to get a continuous function. If you subtract them, f minus g, right? If you multiply by a constant, so k times f, that will also be continuous. If you multiply the two functions together, that will be a continuous function. If you divide the two functions, that will be continuous unless g of a is equal to 0. I mean, if you try and divide by 0, then you're going to be creating problems. But if the denominator is not 0, then you'll have continuous functions. Right? There's other things you can do as well that don't have quite the same setup. This has to have f and g both continuous at the same point. If I want to do something like compose functions together, then I've got to be a little more careful. So if I say something like, if f of x is continuous at x equals b, and limit, well, let's see, and g of x is continuous at x equals a, with the limit as x goes to a of g of x equaling b. Of course, because it's continuous, that's also g of a, right? But so the thing I want to do is I want to look at the composition. I want to look at what is f of g of x, right? Is that a continuous function? Well, the thing is, I'm going to let x go to a, then g of a is going to go to b, and so then I'm going to be looking at f of b. Well, if f is continuous at b and g is continuous at a, then f of g of x is indeed continuous at x equals a, okay? So the composition of continuous functions is continuous. There's also the matter of, you don't necessarily need both of these continuous, but if I look at the limit as x goes to a of f of g of x, I can say that's equal to the limit, sorry, f of the limit as x goes to a of g of x. I can do this, right? This is as long as f is continuous. At whatever this limit is. Right. Now, g of x may not be a continuous function, but as long as this limit exists here, then, and f is continuous at that point, then you can slip this limit inside or outside of the function. In fact, I claim we do that all the time anyway. I mean, if I asked you, what's the limit as x goes to a of, sorry, as x goes, let's pick an actual number here, x goes to 3 of the square root of 2x plus 19, what are you going to do? You're going to say, well, you know what? If I plug a 3 in there, 2 times 3 plus 19 is 25. So, hey, this is the square root of 25, which is 5. Well, really what you've done is you've said, hey, I know how to take the limit of a linear function, whoops, 2x plus 19. I know how to take the limit of that thing as x goes to 3, and then I'll just take the square root of the answer. Right? That is, you took the limit of a square root of something and said, well, I'm just going to take the square root of the limit. Right? That's okay to do because the square root function, right, the graph of the square root function looks like this, and 2x plus 19 is headed to 25 here, and the square root of 25, there's nothing that goes wrong right there. I draw the graph, never have to pick my pencil up, so it's continuous at that point, right? And the value is 5, the limit is 5 there. So you've probably already done this kind of thing and not realized that it's legal to do, but as long as you're dealing with a continuous function, you can take the limit inside of it or outside of it. Right? So there's a lot of functions that are combinations of other functions. If you've got a function that looks like this, x squared plus cosine x, is that a continuous function? Is that, let's say continuous function, is that continuous at all of the points in its domain? It's like, well, x squared is a polynomial. We already argued in the previous, or at least stated in the previous video, that polynomials are continuous. Cosine of x is a nice trig function without asymptotes. It's continuous at every point. So no matter what x value you choose, the polynomial is continuous, the trig function is continuous, and you're adding two continuous functions together, so you get a continuous function. Yeah, I don't need to do any proving of limit as x goes to a or anything. Just I'm adding two continuous functions together, I get a continuous function. If you talk about dividing them, if I looked at let's say g of x is cosine x divided by x squared, is that a continuous function? Well, with the divided by, there was one proviso, right? When I was up here and I talked about these things are all continuous, unless you happen to have a spot where the denominator is 0. So this thing right here, cosine is continuous everywhere. X is continuous, sorry, x squared is continuous everywhere. So this function will be continuous everywhere, unless, of course, you're trying to divide by 0. So this is continuous except at x equals 0. Because that's where the denominator might be 0. So anyway, there you go. You can combine continuous functions and get more continuous functions.